Okay, morning everybody. So let's start with a little bit of recapping what we said the last time. So I told you I would tell you during the two first lecture about these two systems, so the rolling colloids and the walking grains. And so last time we concentrated on the rolling colloids. So remember we consider isolating spheres that are sandwiched between two conducting plates. And you can actually design the kind of track in which you want your rollers to roll by just having a scotch glued on your conducting plate so that most of the plates they are isolating. And then in the regions where you have cut the scotch, then it's conducting. It's very convenient that because of this, there is actually a gradient of electric field in the parallel direction between the place where it's not conducting and the place where it's conducting, and it happens that this is repelling the particles towards the inside. So if we have some kind of virtual electrostatic walls that confine the suspension within the track. Okay, so then we spent some time discussing how these things were rolling. And so remember, it's an instability, so you don't have to engineer the colloid to have a head and a tail. You have a spontaneous symmetry breaking. That's a major difference with most usual active systems, experimental ones I mean. And so there was a polarization that turned to be unstable with respect to the presence of this external field, and there was a balance between the rotation of the particle and the conduction of the charge, and the relaxation time of the charge, and that sets a steady state where the polar vector is no more vertical. And so you have a parallel component and a perpendicular component, and the particles are rotating. And then there is a complicated calculation to demonstrate something simple, which is that if you roll and you are on a wall, you move with a velocity v. The calculation is complicated because you have to redo all the calculations about the location of the charges and the hydrodynamic forces, etc. But otherwise, the principle is really very simple. And remember, we had a formula telling you what was the velocity as a function of the intensity of the applied field. And this formula is the red curve here. You had a square root of something like E minus the threshold field to the square minus 1. This is this curve here. And these are measurements of the velocity of isolated rolling colloids. And you see that it works perfectly well. Okay, so that's the simple electrostatic and hydrodynamic theory, and we were very much helped in the fact that because there is this perpendicular component of the polar vector, we have dipole-dipole repulsion, and the particles always remain at quite a large distance from each other, a few diameters, so that we don't need to do with lubrification theory or very close interactions. Okay, so just to recap what was the phenomenology of the system, when it's dilute, you have a dilute gas. And then when you increase the density, at some point you see, so I just show the movie again, you see this very long band of colloids, this front of colloids moving. Note that it's not at all clear that this kind of band are exactly the same solution as the one of the Vicek model, and probably they are not. And then if you increase further the packing fraction, you have a polar state where the particles are moving in all in the same directions. A picture of this can be seen here. If you look from above in a periodic boundary condition track, you see that this band I was talking about is rotating. Note that it has bizarre fluctuation in the tail, which again suggests they are not exactly identical to the Vicek bands. And then on the right here, you have the same kind of things where you could see the rolling colloids moving from right to left, then bouncing on the wall, and then going back again and again. And as I say, this system is, even if it's not a strict realization of Vicek, as Hugues argued, we expect the Vicek model to be some kind of generic in the sense of universality classes. And so it would be nice to use it to test predictions. So for that, we first had to be quantitative, really. So we did all these things that consisted in computing the interactions between the colloids. And the statement were that the colloid anti-align with the parallel component of any external field. If you have a parallel external field, they will anti-align with it, in particular with the external field that is produced by any other colloid. And this external field has a component which, as I said, is related to the dipole perpendicular to the plates. This is this one, and so this will amount to a repulsion between the particles, and then there is the component which is relative to the component that is parallel to the walls, and this one is a dipole, and so you have a dipole field, and again you would align in an anti-parallel way with this field, which is larger distance field. So that's for the electrostatic interaction, and then we made some statement about the hydrodynamics interactions. These one have essentially a Rotlet component which at short distance resemble this, which means because you align with the velocity stream, the colloid would come, and when you see these ones, you see that it would do something like this or something like this. So this is responsible of alignment, and this is valid as long as the distance is smaller than the thickness separating the two plates. And then at larger distance, because you have mass conservation in hydrodynamics, there is a large distance field which is again a dipole. Okay. So all this can be recast knowing that the velocity, that the speed fluctuates very, very little in this experiment, that it does not depend on the fact that the particles turn or not. And this is an experimental fact that we use here. The dynamics is essentially the one of the angles of the little arrows, and it can be recast in this generic form, adding some noise here, a classical diffusion noise. And you see that actually it has a number of symmetries. This is alignment between the two dipoles. This is the dipolar interaction, and here this is this interaction that is related to this repulsion that I was describing before. And all the work that we did allows us to have the precise expression for this radial dependence. Don't write them down, it's not necessary, but the point is that we know these precisely depending on all the microscopic coefficients, the mobilities, the dielectric mismatch, the conductivity of the liquids, and so forth and so on. In blue, you have the hydrodynamics, and in yellow, the electrostatic. We see that the repulsion part is purely electrostatic, as I already argued. And then the alignment is mostly hydrodynamics, because this is the 1 over r cubed term, which is dominating the 1 over r5 term. And here we see that in the dipolar interaction, it's again the hydrodynamics, and of course, the 1 over r2, which is induced by the mass conservation that is dominating. Okay, so this is the equivalent of, in the case of the Vicek model, of saying two particles align plus noise. Okay, so you see in what sense the Vicek model is an effective model. It's integrating all this in this rule. So now we may wonder how much all these things will modify the physics or not. So to do this, you have to do a kinetic theory. This was done at length during the last Michael lesson. Let me just recap, because the scenario is always the same. For all kinetic theory, you do the same calculation. So I think it's a good idea to have them clear in mind. You first start, you have your Langevin dynamics. Well, if you start from a Langevin dynamics, yes, Hugues? This is the screening. You can do an exponential one, or you can do 1 until the distant n, and then 0. You mean I wrote the theta function the wrong way? Yes, okay, you see what it is. Okay, so so now I said you start, let's say, from a Langevin dynamics. You could, of course, start from an Hamiltonian dynamics. It doesn't change much of the story, except it's a little bit harder to write down the Fokker-Planck equations, but which are then called the Kramers. But anyhow, you start here from n Langevin equations, and it will transform in an exact manner in an n-body distribution with a Fokker-Planck description for this n-body function. But of course, this n-body function is much, much too much information. And so you integrate out n minus 1 particles, and you end up with an equation for the one-body particle. That's the first step. This first step induces a problem, which is the fact that it depends on the two-body particles. That's the first closure issue of all kinetic theories. Here you can do some kind of approximation. Boltzmann did something very simple. He did just something like this. Psi2 equals psi1 times psi1, so an hypothesis of no correlations. This is the Kao molecular hypothesis. Here we include the fact that, of course, the particles cannot be within the same diameter because they cannot overlap. Enskog added the fact that you need to transfer momentum from one particle to another, and that leads you to another closure, okay? But these are essentially the main closure. Well, there are some others, but anyhow. So here we take this one. This allows you to have a closed equation for this function psi1, which here I've noted psi, which I wrote here. Actually, you can decide to work at this level. You can put this in a computer. It's a bit tough, but it's an integral differential equation, and you can solve for the distribution of the one-body particle. This will allow you to test this part of the hypothesis. Okay? In active matter, I'm not aware of work which has really done that. In granular media, this has been done thoroughly by people like Bray and others. Yes, Hugues? Thomas Hilo, yes, of course. When checking the difference between the Enskog and the non-Enskog stuff, etc. Okay. Then you want to describe long-range hydrodynamics fields. That's always the same procedures. These things are written, I think I've been written already 3 times this week. You define your average density field, here your average polarization field, and this nematic tensor, which are several successive orders in the moments of this distribution, which is a distribution of this orientation of this vector P, actually, which is a unit vector here. It's a unit vector because I consider the speed is not fluctuating, and so I can set it to 1. This is important. The theory is much more involved if you want to include velocity fluctuations. Then you enter classical hydrodynamics, which is already difficult when it's not active. Okay? So this is a key assumption in all kinetic theories of active matter so far. Okay? So you define these fields, and you want to write down equation for this. So you see, you have an equation for psi1. You just need to integrate it over theta to have equations for these. For phi, it happens to be very simple because there is no other dependence on theta but psi1, and so you have always the conservation of mass that comes out without any approximation. However, for pi, you end up with a functional that is complicated in phi, in pi, and in q. And then for q, you have a functional, it's also complicated, that depends on phi, pi, q, and higher order moments. And that's the problem here. So you need a closure. There are many schemes of closure. You can do some kind of systematic Fourier expansion, and maybe Hugues will discuss this a little bit, and then having some kind of scaling arguments, check that it's self-consistent, etc. And it's a tricky work. Anyhow, one way of doing is instead of making really closure on the moments of the distribution is to make assumptions on the distribution itself. So what you can say, but if you do this, and this is important, you cannot do the same assumptions if you are close to the isotropic phase where all particles are moving in all directions, or if you are close to the polar phase where all particles are moving in the same direction. Obviously, the distribution of the angles will not look the same. So close to the isotropic solution, well, you say, well, it's almost isotropic, so the distribution should be almost uniform, 1 over 2 pi in 2 dimension, 1 over 4 pi square in 3 dimension, and then you just make an expansion in the variation of the angle, so that's the linear, the only linear things that is compatible with the fact that this integral of psi1 must be the average orientation. Okay? And when you do this, okay, you inject in all this, you have to massage a little bit all this, you end up with an hydrodynamic equation that is closed for this pi vector. In our case, we have it here with this alpha that depends, alpha, beta, that tau, kappa, that depends on all the microscopic coefficients. Okay. Now, if you are close to the polar phase, you will do another assumption. You will say, well, close to the polar phase, mostly all particles are moving in the same direction. So then I will say this is essentially this my distribution, a delta function pointing in some direction plus some Gaussian fluctuations. You can do this. And if you do this, you will end up with another hydrodynamic equation. That's important to realize that the hydrodynamic equations differs whether you are in the isotropic or in the polar phase, because you describe the physics around these basic states. And you can see here everywhere the 1 minus pi pi that tells you that you are developing in some sense around the case where you are magnetized. Okay, we have hydrodynamics, as Mike says, then we can do linear stability analysis, we can do hydrodynamics. This is something we know since more than a century. So let's do it. to see, I mean, we don't do all this calculation for the fun of it, at least not me. So near onset, there is a very easy calculation that you can do. You are near onset, so you know you are close to the isotropic solution, and say, okay, let's look for a solution that does not depend on space. Super easy. I remove this gradient, I remove all these gradients, I remove all these things here, and the only thing that remains is tau dt pi or phi pi equal something here which is proportional to phi pi and minus phi pi to the cube. So this is just a usual Landau-like expansion for the magnetization. It's super easy to solve. You will, of course, find a square root, and that gives you a prediction for what is your polarization just at threshold. Unfortunately, you cannot test this experimentally. Why? Wake up. Why? Because close to threshold, you don't see the solution, the homogeneous solution, you see the bands. So you don't see this solution. It's unstable, which actually you can also check and compute. Okay, so if you do the linear stability analysis of this solution, you can find that it's unstable. Okay, but then you don't see it, it's unstable, it's consistent, but it's not really a strong check of the analytics, right? There is something you can do, though, is let's imagine we are still close to threshold, so that the average polarization is still small, otherwise we cannot use that hydrodynamics. And let's consider these bands. And then we can make an assumption, well, not an assumption, we can look for a solution which is a traveling solution. We just say that the polarization and the mass are both traveling, so you have an equation in 1D, so you put yourself in a 1D context, and you say that you have a traveling solution that is a function of space minus some velocity times t. Then you can look for solutions of this, and you can make a prediction for the polarization inside the band as a function of the of the density inside the band, where phi infinity is the density of colloids far from the bands. And so you have some kind of a close relation between the two, and this you can measure experimentally, and this also, and S is the measure of the distance from the front of the band. Okay? And this is the prediction here, and these are all, so you have many measurements, which are all these gray dots, and these are the average, and these are the statistical fluctuations. And that's really good, because there is no parameter that you can adjust here. So, I mean, you're already computing a bifurcated solution, and so forth and so on, looking for propagative waves, and you find something, well, that tells you that at least your microscopic description was good. Now, to test really the theory, we have to really test the hydrodynamics. So this was done in this recent paper, which is this nature material that I was mentioning not yesterday, the day before. And they decided to study the sound propagation in this moving flock. That is, you have to look at density fluctuations in this homogeneously moving flock. Yes? What PD? The which one? Yes, you could do that, of course. No, of course. No, not with all the numbers, etc. No. But of course, you could do that, sure. But I mean, at least we did the experiment for something. But so we want to check how it happens. Yes, of course, you could do that. So now you are around this polar state. All particles are moving, and you are interested in the fluctuations. So you linearize your hydrodynamics equations around this state. Okay, it's a bit boring. You get a matrix. I want just to stress one point, is that when you do this, so if you linearize, the density will just be the average density plus epsilon delta rho. And the speed will be the average speed plus epsilon some speed. But this speed will have a component parallel to the direction of the global motion and a component perpendicular. Okay, so this one here and this one here. So you have to inject in your equation, linearize. You get the linearized equation for rho, for v, and for u. And an important point here is that for u, you see, at that level of expansion, u does not has, I mean, this equation does not have any derivative in time, which means that u is completely slave to the gradients of density. It's a fast variable. Doesn't have any own intrinsic time scale. And this you can check by looking at the waves. We'll look at this in detail. I mean, the sound waves. And if you plot the amplitude of uq to the square as function of qx times rho q to the square, you find something that is linear, which is essentially this equation. Okay? Then you look for your sound waves, you expand, you get a dispersion relation where you have here a linear sound velocity. It's not dispersive, it does not depend on q at this order. And then you have here a dissipation part. Okay, you get the two expressions, and in principle you can test all that. This was already in Turner-Tew's theory, except you didn't have the dependence on all the microscopic coefficients. And so here again is this expression. So you have your polar things moving, and you look at the density-density correlations in time. And you see that indeed there are sound waves and that they are damped. And this is true both for the density or for the velocity, the perpendicular component to the main flow. This is just temporal correlations of the Fourier modes. And yes, there are waves, obviously. And what you can characterize this by looking in the full Fourier space. So these are frequency, these are wavelengths or wave vectors, but amplitude of wave vectors. And you see, well, that you have indeed two branches, and for very small q, you can linearize, and this is the sound speed. Okay, that's... If we make a cut here, so for a given amplitude of the q vector, this graph resembles this. You see the two peaks, which corresponds to these two branches. You can see omega plus and omega minus, which are the two solutions with slope c plus and c minus, and the delta omega tells you something about the dissipation. Let's just talk about the sound of speed. This curve, this continuous curve here, was the prediction of the Turner-Tew theory, and these are the experimental measurements that were performed by Denis Partolot and Delphine Geher. So I think this is really remarkable, because this sound propagation, so this is, let's clarify what this diagram is. When it's the first time you see it, it's not clear. This is the angle in which the sound wave propagate the angle with the main direction of the flock. So these are waves propagated in the direction of the flock. These are back propagation, there is essentially none. You have two solutions in each direction, and these two solutions, this is the amplitude of c that is plotted here. Okay? And this is for one given value. No, this is okay, no, that's it. This is for one given value of the density. You can then repeat this for several values of density, etc. Okay? So I will stop here. So I think it's time for a question about this system. One. So this is one. On this, I have to check. I think this is one, and so yes, they're always slower than. So at small angle, here, yes. But might be, yes, you just have to look at this expression here. Yes, might be. Just to come back to the former question, if you put theta equals 0, this term is 0, this is 1, then you can get rid of the square root. And so I think you get exactly 2u0. So I think, no, this is u0, this is 1. This is the largest one. So when you put a plus here, one is going exactly at the speed of the particles, and the other one is slower in the direction of the things, and then in the other direction it has nothing to do. Okay? Okay. Other questions about this system? So I wanted to recap the scheme of this calculation, which are always very similar. The point that is important is that your closure model depends around which state you want to do them, and that before that there is a kinetic closure about the distribution itself. Yes. Yes. Okay, so yeah. Yes. Uh-huh. No, this is true. So if you look in detail in the supplementary material of the first paper, we do the linear stability analysis regarding really all modes. And there are bending instabilities, there are splay instabilities. The bending instability is stabilized by the confinement. And this is related to all the terms that we have, because of the values of the parameters. So I'm not sure, well, it's not very, no, it's not strongly confined. You have something like a few hundred colloids. Yeah, you have a few hundred colloids in the width. I mean, typically this is why we cannot do this with the grains, is that we never have that. Yes. So that's an important remark. Remember, so it seems that everything works very well. And I don't like to conclude this when I do experiments, because an experiment that says that everything goes very well does not bring any new knowledge. So remember that this is only testing the linear part of the theory, indeed. That's the first remark, important remark. The second important remark is that remember this giant density fluctuation discussion by Hughes with this exponent that is always more or less the same value because it's a combination of two true critical exponents. Here we could never go and test it really seriously. It's fluctuating a lot from one experiment to the other. So as a matter of fact, this experiment has really millions of colloids rolling. It's really large. So it means that if you really want to test the theory in its nonlinear levels and its complicated renormalization effects, you really need an experiment that is even much larger. I mean, there was some example like the pneumatic bacteria, which seems also to be very, very large. I don't know how many bacteria there are in this system, but it must be huge. So it's okay. So I mean, either it says that you need further larger experiments and then you go to build something like the CERN, or that maybe the theory are not relevant for practical flux. There are two ways of saying things. Absolutely, that's right. Yes, I agree. No, yeah, but I agree. So in this one, I guess it's something like 1 centimeter. It's really huge. Are there questions from the non-specialist, please? On which scale what? The dynamic is what? The thickness of the channel and the thickness of the channel. So the colloids are 5 micron and the thickness of the channels is, I think, 50. Ah, yes. Yes. I mean, it's still specialist, huh? Okay? Okay, so let's stop here. That was just a recap. It's already half an hour. So let's move to the working grains. Okay, and again, I will go to the blackboard in a moment, but I want to show you first experimental results. So now you can forget about the rolling colloids. We move to a completely different system. To my point of view, much simpler in some sense. So the idea was to study this propelling stuff, and so we made the simplest generalization of hard disks. So we take disks and then we engineer them in the way that they have two legs, one very rigid metallic leg and one rubber leg, and also more frictional than this one. This one is just a point contact. This one is a large contact with the ground. And if you shake these objects, they will move in an isotropic way, and even in a polar way. So they produce trajectories like this, with some persistence lengths. And because you want to be sure of what you do, you also have particles which are perfectly isotropic, which have a circular contact with the ground. And when you shake those, they look very much Brownian. They don't need to be because it's not a thermal system, but we studied all the statistics and they are really pretty much Brownian. Okay, so these are our elementary objects. And then we put a large number of them on a vibrating plate. The vibrating plate must have been set in such a way that you are sure you are really vibrating perpendicular, I mean parallel to the gravity. This is tough. And also you want to be sure that your vibration is homogeneous in amplitude. And in our case, it was homogeneous up to a few percent, which is also tough. So if you vibrate the isotropic particles, what you get is a nice hard disk liquid. The color here is just indicating the direction of the displacement between two time frame, two image. Now, if you put exactly the same number of particles, which is here typically 1,000, a little bit more than 1,000 on the frame, and you vibrate it, this is what you see. So obviously, the fact that the particles have some persistence length in their motion change completely the physics. First, the density is not homogeneous, obviously. They condensate a little bit, and they seem to go together in some directions. Okay? You can quantify these things. And when you quantify these things, well, you do what we all do. You compute this psi of t, which here is not the same psi of t as before. That's okay. This is really the magnetization. Okay, this is the modulus of the total momentum, the average momentum. And you see that, okay, there is a control parameter in this problem, which is the amplitude of the vibration. And we change only the amplitude of the sinusoidal motion. We don't change the frequencies, because changing the frequencies is delicate, because then you enter into resonances of your whole system, and this you want to avoid. So you change the amplitude of the vibration. So what do you do when you do this? You do two things. This I should write here. Of course, if your amplitude of vibration is too small, you don't move. So as a function of the amplitude of the vibration, which here is so the amplitude omega squared divided by the gravity, there is a regime where so here is the typical velocity of the particle, assuming you can define one, and okay, this we checked. You have, it doesn't move, and then for gamma larger than 1, it starts moving, so it gets some velocity, but you can imagine that you will not increase your velocity forever just by shaking grains, right? I mean, at some point you dissipate more than you inject. So this will saturate to some value, and that's something like this. Now you do another thing when you vibrate. If I shake you too strong, you will lose your sense of orientation, right? So the orientation of the particles, or let's say I measure the rotational diffusion of the particle, let's say some kind of dr, this is not a good color, some rotational diffusion, then this one is also very weak here, although not really zero. And this one grows and grows and grows and grows like this. This one, I mean, has no really reason to saturate. You shake more and more. And so as a result, the persistence length of these systems, psi, which is just some things like V dr, or divided by dr. No, yes, dr. Divided by dr, I always make the mistake, thank you. Is something that in this regime where the velocity is constant is essentially a decreasing function. And then here, okay, at some point, it has to go to 0 because the velocity goes to 0. And this happens on a quite tiny range of vibration amplitude, and that's not very convenient for experiment. So all the experiments will be done in this window, where increasing the vibration doesn't mean accelerating the particles, but means increasing the noise. Okay, so decreasing the persistence length. So when you do that, so here you are at large noise, and you have essentially 0 values. So this is the temporal signals and nice tiny fluctuations of the magnetization. And then when you decrease the noise amplitude, you see that the average value of this is growing. Here it's so here it's close to 0. Here it's growing close to 0.2, and then here it reaches something like 0.5. And the fluctuations also are much larger. And you can look both at the distribution of this value, and indeed, when you if you increase the amplitude of the vibration, you start from a point where you have an average value of the magnetization with quite a large distribution, to a magnetization that goes to 0 for large noise. And this is just the average value that is plotted here. And this, for reference, is the one that you obtain for the isoparticle, so that is essentially 1 over the square root of n. For which one? I don't have plots of this here. This has been characterized at length. We did all the statistics of these little bodies. I can give you this later. The isotropic one are really Brownian-like. The other one, they have the rotational diffusion is really diffusive. That's why we can define this rotational diffusion constant. The statistics of the displacements are a bit peculiar. They are not Gaussian, although you have no correlation in time, etc. So it's a bit special. Okay, so we can be more precise by computing correlations functions. So again, these are experimental data, hence the fact that I used the projector. Here you see a nice flock, and you can compute the spatial correlation function or the temporal correlation function. When the noise is large, well, they decrease more or less fast. And clearly there is a change of behavior when you decrease the noise. You see, here it goes to some kind of plateau. This is in log-log. And here this is in log-lin, so here it's more like exponential, and here you see the curvature has changed. But you also see that the system is not so large, and that this is typically, we don't, of course, when we compute these kind of things, we set ourselves in some kinds of region of interest where we don't feel the effect of the boundaries. We check that the density is homogeneous on average in these regions, etc., etc. And so it's not so large, and so it's not so clear to conclude whether really the system would have long-range correlations or not. This is in diameter of the particles, you see. So the region of interest, which I plotted here, must be something like this. The persistence length is of the order of 7, depending on the vibration, of course. So for the most persistent, sometime we could reach 10, and then for the less persistent, it goes down to 1. Oh yes, when you really have a lot of noise, actually, I mean, they are still oriented, and so you can still see, if you look in details, that the dynamics is not the one of the ISO, but it's not so clear to see. So we could do the experiment Jorge was suggesting the first week by putting these particles into a fish net and then shake them more, which is the same as putting alcohol to the fish, remember? And maybe it would escape the net faster than when it's active, okay? But okay, we have not done the experiment. Okay, so of course, our nice friend, numericians and theoreticians says, come on, the system is really too small. And I agree with them. Unfortunately, so we did some experiments where the plate was the same size. Here we confine in a smaller region, but then you have inhomogeneities, you have other issues. So one way of dealing with this is to try to have a model for these particles and then simulate them. Okay? So this was done in collaboration with Erwin Frey, will be here next week, I think. And Christoph Weber. And here are just two movies. One is the experiment and one is the numerics. Same code, same number of particles exactly, everything has been rescaled. And what we did is actually to propose a model, then use all the statistics I was talking about when I answered your questions about the correlations in time between the displacement, the angles and the displacement. So we have many curves. The correlations are really looked in detail, and then we impose the model to fit all these curves for the individual dynamics of the particles. And then you cannot touch the coefficient of the model anymore. And the only thing you do is to change the density. Okay? And so, well, it was a good reproduction of the reality. I'll come back, of course, to this model when I will switch off the screen. And then that's good, because then you can increase the system size. And you can do periodic boundary condition. And so this is a movie in periodic boundary condition after a while. And then you see that indeed you have a true polar motion that sets in this system. Okay? Note that it's not a Vicek-like system at the individual particle level, because these little blue here, which are fighting against the red, finally they will eventually turn back and become red. But in the Vicek model, it would never survive so long. You are surrounded by 6 guys which are definitely red, woof, you would rotate plus some noise. So the fact that there are all these isolated blue shows you already that the microscopic dynamics is not exactly the same. And so it's interesting to wonder if it's important or not, in the sense of what Hugo was discussing. This is the phase diagram that was obtained. Without too much detail, this is the amplitude of this is the packing fraction. And this is essentially the amplitude of the noise, which will be the only parameter that we tune in the model to study this phase diagram. And here we have a disordered state. Here we have an ordered state. Here there are bands. You need to make a very large simulation to see them. Here there is a bizarre state I will not talk about. Okay. And there are some giant density fluctuation in this phase. Okay. So the question here is, why do these things reproduce something similar to the V-check scenario? Why do these things align? There are disks. And they collide essentially elastically, as we could check. So why do these things align? I mean, that was completely unexpected that there is alignment here. Okay. Second, these things, when it's really dense locally, they must slow down on average. So there must be some kind of crowding effect, and so some kind of motility-induced phase separation that could explain this group that we could see. So it might be a mix of this phenomenology that I was describing. Is this important for the description of the system or not? These are still questions that are open. And then, of course, as I said, where is the alignment coming from? Okay, so these are the questions I will now try to answer on the board. Yes. Now climb. This is you. Okay, good. Some coffee. Okay. So, you remember this? So although the system looks simple, I mean, the motion is related to the friction with the ground, etc. And this is actually much more difficult to describe than electrostatic and hydrodynamics. So no way that we are going to do a true 3D mechanical model of the system. That would be bound to failure. So the model that we're going to try to deal with is to say, okay, let's say these things have to obey some Newton law. And so we should say something like m for each particle dvi over dt equals some active force in this direction of the particle. That depends on its angle. That's for sure. And then there must be some damping. So here we have different options, and we played with that. It seems it's not so much important, so let's put some kind of more like viscous damping. It can be I mean, it's frictional, but it depends on the linearly with the velocity. Yes, and then there can be noise. And then if you do this, and you try to simulate this system, then of course you have to add interactions. So elastic collision. Eventually you can say they are slightly inelastic with a coefficient, restitution coefficient, which is slightly smaller than 1 if you want to be a little bit more realistic. And then you want to put some equation on the noise. And here I do actually what Yari was doing. I also take some over-damped dynamics for the angle. It happens for the numerical simulation, it is much helpful. And okay, naturally you would put some noise. Some rotational noise with amplitude dr. And that's it. So it's a little bit more than an ABP. It's actually the model that Yariv was introducing when discussing in its last lesson, using the inertial term to see the importance of the momentum. It's very similar to that. You put this in the computer, no collective motion, obviously. Why would there be any collective motion? The things have no reason to align. Okay, then you can argue, yes, but there might be friction at the rotation, etc., etc. So then we looked at this in the experiment. The particles are not turning at the collision. They are not rolling on each other. So that's not the reason. On the contrary, there's something that we could notice, and I remember this discussion. Hugues was there in the coffee room of the lab in Saclay. And we were playing with little objects that we were sliding on the ground, and they were colliding each other and walls. And so you can imagine what they were, right? You know, beer caps and these kind of things. And we noticed that if you draw an arrow on an object and you send it by gliding on the ground, it hit the walls, it bounces because the collisions are essentially elastic. What about the arrow? It's the same. So it means here we have the velocity that is like this and the arrow that is like this, while here the velocity and the arrow, because we throw them in a careful way, were aligned. So this is the first important point to remark, and this is generic for true active matter system which have a polarity embedded in the particle. It's not the case for the rolling colloids. Remember, that was a different case. The velocity and the orientations are not always the same. So it means when we see in the V-check model, when we say that V equal n, essentially we overdamp this, there is no inertia, and then V equal n. Okay? But this is not true, obviously, for this kind of system. Yes? Yes? Yes. Indeed. So then you try to think about, I want to engineer some particle that is self-propelled. So I need to break down the front tail symmetry in some way, and this is n. And in our case, we did this by having a rubber here and a little tip in the front. And, well, the velocity, let's say, is like this. But of course, after the collision with the wall, as we said, it's not the case anymore. The velocity will be like this. And now you see that because we engineer the particles in the sense that they are not chiral, that is, there is a strict left-right symmetry of the propulsion mechanism and the dissipation mechanism with respect to n. When V is not aligned with n anymore, there's no left-right symmetry. You clearly see that with respect to this axis here, there is much more friction here than here, for instance. And so there will be a torque acting on the particle, the single particle. So there will be here a term, a torque, gamma, that acts on the particle and that depends on the angle between V and n. Okay. So that's the very important ingredient of this system. And once you have this torque, you already understand that, for example, this system will not have an equation of state, even if it's hard disk. So it's almost like active Brownian particles. But because of this torque, at the level of the single particle, there will not be any equation of state. And this is something I will discuss in the next lesson. Okay? Because you remember the talks by Yariv. Okay. So now, let's have an idea of what is the dynamics when we collide with this wall. When we collide with this wall, and this is actually what we would do ourselves. When we collide with this wall, the velocity is like this. Now this is the new initial condition. And because of this active force that acts like a gravity field in this direction, this will be bent progressively. Something like this. And it would be bent until you recover the initial orientation if nothing else was going on. And the system would be extremely boring. It would collide the wall again and collide the wall again and collide the wall again. Okay? Note that this is exactly what ABP are doing. They collide the wall like this, instantaneously. because v is equal to n instantaneously. Here there is a time scale, tau v. Now n is turning because there is the torque. N is turning towards the velocity. So because of this, while the velocity is approaching n is approaching v. And so you will end up with a trajectory which will be something like this. And you will exit the collision with the wall or not. That will depend on the the ratio of the time scale that is here, which is related to the ratio of, well, you have to make this equation dimensionless, but of course there is a time scale here. Let's call this one tau n, this one tau v. The ratio of these two time scale I will call alpha, will control the dynamics of the collision with the wall. If alpha is large, it means n is very persistent. If n is very persistent, I will be closer to the orange trajectory. And if alpha is very small, I will be closer to an elastic collision where n would instantaneously go towards v and I would just bounce like this elastically. In between, I have some angle here, theta out, that is a function of alpha, and a function, of course, of theta in. Theta in was this angle here. And you see that theta out is always smaller than theta in. So the particle has a line with the wall, in some sense. This is the hand-waving argument of why those particles align. They align with the wall. So now if you want to deal with collisions between particles, you have to deal with two disks that collide. The collision is not, of course, a collision with a wall. You will have the cross-section between the particles that will matter, where you hit the particle, in front, in the back, in the bottom, on the side, what is your orientation when you collide, and so on. And this is what we are going to compute now. So we are going to do the Boltzmann kinetic theory for hard disk that are self-propelled according to these equations. Okay? Yes. Yes. And this was used to set the parameters of the model. But it's here. So precise the question? Is this one? That's the one that bends the trajectory here. No, at the end, oh, sorry, maybe it was not clear. So at the end, V and N are again aligned. But V has turned towards N, but that's just because of this equation. And that's the propulsion force. You want to go in the direction of N. That's the orange trajectory. But N, in the meantime, rotates towards you, and so you end up with some intermediate angle. Clear for everybody? Yes? Okay. Absolutely. The dilute phase cannot be described by ABP, as we will see by the fact that there is no equation of state for this system. Next time. Questions? Yes. Very good question. Here I really need it because I put here hard disk elastic collision. So there is no time scale here. And so I need inertia already. However, this equation happens to be n equal v all the time because collisions are instantaneous, because I put hard disk collisions. In reality, collisions are never instantaneous. Then I could get rid of inertia, because otherwise I set n equal v and this equation decouples. So I need some time scale in the first equation. Can be the collision one, could be a potential one. This is some work we are currently doing. And then the inertia is not important, but I need some time scale. Other question? Okay. So now we have said that it aligns. Now I would like to give some more physical sense to this word alignment, because in a matter of fact, we always talk about alignment. We say it's the fact that the angle reduces, etc. But I mean, how does it come out when you write down the hydrodynamics equation? Where is the alignment in these hydrodynamic equations? You have many coefficients. You know that there is a linear term that amplifies the magnetization, a cubic terms that damn the magnetization, but where is alignment and what is its expression? That would be nice to know for a generic system. Okay. In physics, when we say a word, we like to put a formula nearby, right? To say what it is. Okay, so let's forget for the moment about the model. And let's consider the following setting. So I said a very important thing is that the momentum is, forget about the mass, is of modulus V0, which is a constant. There are no fluctuation of speed. So let's set this to 1 for any particles. Okay? When we are in the steady state, of course, of the particle. Then we define large P, which is nothing but 1 over n, sum over the momentum of the particle. This is a vector. Okay, and we will be interested in a quantity which is essentially the modulus of this large P, which I called psi in the slides. And this is essentially the magnetization. I'm summing all the unit vectors. And then I take the modulus, and if it's disordered, it's 0, and if they are all aligned, it's 1. And so I'm essentially interested in the following question. If I start with a disordered state, where psi equals 0, and there are some fluctuations, will this quantity grow or not? That's the question, whether I will have a chance to have a transition to collective motion or not. If it's them not to grow, then it will remain isotropic, right? So essentially, I want to know zeta psi at very first order, without any gradient, without anything. I want to know if this quantity here, this number, once I have integrated over all the statistics of the problem, is a positive value or a negative value. I'm at the purely linear level here. Yes, of course. No. You mean truly subcritical, globally subcritical. I'll discuss it after, okay? So what Hugues is referring to, you have psi, you have a 0 psi state, and so you wonder whether something else can happen. So there are two scenarios, several scenarios. One scenario is that at some point this becomes unstable, means this value goes from negative to positive, and then there are several scenarios. You can bifurcate and have a nice continuous transition here. Then, depending on the sign of the second term, of the next term that is tolerated by symmetry, you can have this saturation, but this, if this now is negative, you will need even another sign, another term. So you can have this scheme, which corresponds when psi is positive. You can have something more like this when psi is negative, and then we have here a coefficient that finally saturates things. And it can be worse, etc., right? That's one scenario. There's even a worse scenario, which is that, and this is what happened in the Vicek model, there exists completely nonlinear solutions. Here we are looking at weakly nonlinearities, but you can imagine that there are solutions in phase space anywhere. Okay? And then these solutions, if you are not considering purely homogeneous phase, you can jump to them. This is nucleation. And this is what is actually happening in the V-check model when the system is large. Okay? So this is indeed a possible scenario. We'll come back to that. So, oh yeah, okay, oops. Okay? Yes, it's true. Yeah, it's true. And this can be a hub where it's rotating or not, etc. It's a sketch. It's a sketch. This is called supercritical bifurcation. This is called subcritical bifurcation. This is called globally subcritical bifurcation, in the sense that you don't connect to your branch. If you don't connect to your branch, any expansion description of your problem is bound to death. Yes. Don't. Okay, this is really another story. I did my PhD on this. Yes, you can have a linear instability somewhere. Then this one can be earlier or not. I mean, all these scenarios are possible. So if you think about hydrodynamics, you have the Poiseuille, the plane Poiseuille flow. Yes, the plane Poiseuille flow would have here a transition at some Reynolds number 5772. And then you always transit by some finite amplitude perturbation to something else before. But if you are very careful, you can go to there. Then you will see the Tonmian-Schichling waves. They will be unstable. You will reach these turbulent states. You can come back, and we would see this. All this is perfectly true. Okay, let's come back to our nice walking grains. Okay, so indeed, by seeing this, I'm making an expansion, so I'm supposing that there is something interesting close to psi equals 0. Otherwise, okay. Where are the white chalk? Here. Okay, so, oops. So this is what I want to answer. So what do I have to consider? I want to know if this thing is going to grow. So essentially, I have to consider two particles that are coming, P1, P2. Pop, 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 pop. They interact in some fashion, in some way. Could be a V-check way alignment. For the moment, I don't precise anything, any kind of interaction. And then they come out. P1 prime, P2 prime. But I insist, I will call this a scattering event. Here, P1 equal 1, P2 equal 1 in modulus, because they had all the time to be in their steady state. We are in a dilute theory, so all the particles have a long time to do what they have to do when they are alone. And I consider that the scattering event is over, where again, these modulus are equal to 1. Otherwise, the scattering event is not over. Let's consider a very simple example so that you understand very clearly this statement. No, later. So then I can introduce P, that is P1 plus P2, the total momentum when I come in. Actually, the modulus of this, if this is the incoming angle delta, so P will have, okay, the modulus of P will be, I will need this later, so let's write it down. 2 cos delta divided by 2. And P has some orientation, which I will call theta bar. You see, this P here is not horizontal. It can come like this. It has some angle theta bar. Okay? And with respect to what am I measuring this theta bar is the fact that I will consider that this average, this P here, is not strictly 0, because otherwise there would be nothing. I need some fluctuation of some kind. So this P here has an angle that I set to 0. So this is my reference angle. I have some fluctuation in the P. This is the average P. Okay, I take my whole system. The average P is not strictly 0. Okay, instantaneously. I'm doing really instantaneously here. So the average over the particle, instantaneous value of the polarization is not strictly 0. That defines the direction, which I call 0. And now I consider one pair of particles in the system, and it has some total momentum, little p, that has some angle with this average orientation of big P. Okay? And there is also a difference of angle between the incoming particles. Good. That's the setting. Now, after the collision, I will have P prime equal P1 prime plus P2 prime. And I will be interested in the following quantity. I have little p. I have P prime. Let's make it a little bit longer. And now you see P prime, I can project it on this vector here. No, it's not the P prime, sorry. This is delta P. Oh, delta P equal P prime minus P. And I can project delta P on P. And this will define P scalar delta P. Okay. Good. So this is really the setting for scattering event. Let's take a very interesting example to really understand what I mean by scattering event. Consider two particles that are active disk, active hard spheres. They have a much simpler dynamics than the one I was talking about with torque, etc. There is nothing of this. They are just inelastic collision. In an inelastic collision, the momentum is conserved. You agree with this? Come on, wake up. Yes? The momentum is conserved. What about delta P then? Who thinks it's 0? Only 3? Who thinks it's not 0? No opinion. 1? Well, there are not many votes today, eh? Come on. Okay, then I have to give a dictatorship answer because you didn't vote. So you should vote, you know. So delta P is not 0 because delta P is measured once you have recovered your nominal velocity, not just after the collision. So if you have inelastic particles, they collide. I will don't do the calculation. They have to conserve momentum, but they have lost speed. So to conserve this incoming momentum, they have to restrict the angles. Okay, you know that's inelastic collision. So the angles now are smaller. Well, theta out is smaller than theta in. I made a symmetric collision to make the story easy. This is the momentum conservation that have enforced these angles. Delta P equals 0. This is just after collision. Now I'm active. Because I'm active, I will not tolerate my velocity not to be my nominal velocity. Now I'm free, and I will relax my velocity to the value that balance the active force and the dissipation. And so I will end up after a while, a relaxation time, with the velocity of modulus 1 in the angle that was prescribed by the momentum conservation. But the momentum is not conserved on the long times because I can take momentum in the substrate. This is the essence of being active dry. Okay? And because of this, now if I compute delta P in this final state, obviously P has increased. Is it clear for everybody? This is super important. So when you deal with active matter, there are processes that leads you to a nominal velocity. That's what Witschek says when he says the speed is V0. This is not true for Brownian particles. This is not true for hard spheres in a gas. You have a Maxwellian distribution. Here you have a delta function. This is a very, very strong statement. Kinetic theory with a delta function of the velocities is very different from kinetic theories with a Maxwellian distribution. Okay, there is no kinetic fluctuations. So, okay, so this is really important. And so there is a time scale that allows you to recover this speed, and you have to wait for this time scale to be over if you want to compute my P delta P. That's the important statement. Okay? Otherwise, my velocities are not 1. Okay, so I think I made here all the important statements, and now there's a little bit of calculation. Are there questions here? This is really what you need to really understand. Why? Normal disk cannot accelerate here. You need to take momentum in the ground. Now, these questions are really the key ones. You could imagine another model. Yes. Here, no, it's true. Here I just make the simplest statement here. I take disks that cannot change the angular momentum. They collide elastically. They are inelastic collision. It's not the model that I will describe later. It's another one. They collide inelastically because of this change the angle. The momentum is conserved at the collision. Delta P is 0 just after the collision. But just after the collision, your velocities are not 1. So you have not relaxed all the process. So you cannot do your kinetic theory. Okay, you have to wait. And if you wait, then delta P is non-zero. Yes. Sure. Okay. But for what I said at the beginning, so setting up this, computing P delta P, this I can do for any kind of scattering event, including the one you are discussing. Here I will be able to put any property. Yes? An extra with compared to what? Yes, or the, exactly, yes. Yes, that's the point. During the break, because otherwise I will never succeed in going further, we can think about what ABP would be doing if they were having hard disk collisions. You would realize it's a very ugly model. Okay, so, sorry, but I don't really like ABP. You may have understood it, but okay. So we need to compute this growing thing. Or not growing, but the evolution of psi, which is the modulus of P. Okay, and so there will be two kinds of events, right? There is noise in this problem, so there will be kicks, even when the particles are alone, and then there are scattering events. So if you take, as a matter of fact, any quantity, any observable A of t, that would be the integral over all the possible angle of the distribution of the angle of the particles at a time t times this quantity, the value of this quantity for this angle theta. Then you see that if you have a diffusive event, it will change eta, it will change, sorry, A, did I say eta? A by a small amount. So a diffusion event will induce some delta A diffusion. And to know by how much the large A change because of all these possible events, you would have to compute something like, you would say something like dA over dt related to diffusion would be the rate of these diffusion events. So these are the rates of these random kicks that you give to the system. And then you have to integrate over all the possible events. So all the possible angle, the distribution of the noise that describes your kick, and then by how much each kick has changed your little value A. That's, I think, very clear, right? This is very simple. Now, this is the same for scattering. So this is what is related to this diffusive random kicks events. And that would be the same for scattering. There will be a rate of scattering, frequency of collisions. And then you will have to integrate over all possible collisions. Okay. So collisions have two angles, theta 1, theta 2. Okay. because there are two particles for a collision to take place. And I will reparameterize this problem not by theta 1 beta theta 2, by theta bar, which is the average theta 1 plus theta 2 divided by 2, and delta, which is the incoming angle theta 1 minus theta 2 divided by 2. Or not divided by 2, doesn't matter. Okay. So integrating over all the possible incoming collisions, then the collision can be complicated. I mean, if you remember your cross-section calculation, you know, that you did at some point in your studies, it's a bit of a nightmare with the solid angles. We never like this when we are students. But there will be parameters that describe the collisions. This is called the cross-section, and I will generically call it zeta. Okay, so here in the case of disk, it means, do I collide the disk? So if this one is static, what is this cross-section here? Okay? Is it a frontal collision, a side collision, and things like this? It's a bit of geometry. It's boring and annoying, but it's quite easy. You can find it in many places. Okay, then of course there is, what is the probability of having a collision with some incoming angle and some of this parameter? This is called the kinetic kernel. I mean, this is some function, depends on the kind of system you are considering. And then you have to have your particles that are coming with some angle theta bar plus delta over 2. The other particle must come with the angle theta bar minus delta over 2. And then there is the change of your quantity that happens during the scattering event. And here, look that I have already factorized the two-body distribution in the sense of Boltzmann that is making the molecular chaos approximation. Good. This is the first statement. Yes? Any quantity could be, well, the mass will not change, but for example, my orientation will change. Then I will precise. At the moment, any quantity, and then I give a kick to the particle, and it changes this quantity. Let's precise now. Now, let's say it's just, for example, the orientation of the particle. Then I give a kick to this particle, a random kick, by change this orientation, so the particle has, this observable has changed. That's what I would call delta A diff. Say that again? Each kick will change A by a little amount, because A is the sum over all the particles in some sense. Okay, so each kick will change A by a certain amount, and if you want to know how the total A is changed, you have to integrate over all the possible kicks, and that's what I write here. Okay? Okay, so we have this. And now, yes? Because for the moment, well, it can depend on the amplitude of the noise, for sure. I don't know what I'm doing yet. I don't know what is the observable here. We'll see that in simple case, but in principle, it depends on the state of the particle. I have a particle, it has a state, I make an observable that measures something about the particles, I give it a kick. It changes the observable, it depends on the state and on the kick. This is the most general statement. Okay. So we have this. How much time do I have? 20 minutes? Yes. Oh, no. It's more like 10, right? Ah. Okay, so you're lucky because if I have only 10 minutes, there will be less calculations. So the point is to apply this to the change of momentum. So by how much does, so first let's consider the diffusion example. This is the simplest one. So I'm interested, I have my little a now will be my little vector p for the particle, for any particle with orientation theta. No, the modulus is 1. And there will be a kick. Oops. There will be some change in P. And if it's rotation diffusion, I can describe this by a rotation matrix of amplitude eta applied to P minus the P I had before the rotation. Okay? So this is, yes. And you see that, indeed, this is what I do to the particle is independent of theta, to answer your question in this case. By how much the particle will rotate does not depend on what was its orientation before I kick it, for this model of kick. So then, injecting this here, this now does not depend on theta. And you see it becomes super simple. I can do the integration of theta independently. This is 1, because it's a normalized distribution. And so I just have to integrate over the noise this function here. And so I find that, let's write it here, that 1 over lambda diffusion dA over dt, dP over dt for diffusion is simply, let me write it down this way, minus 1 minus the integral over the noise, the type of noise that I use to kick. Damned. Okay. I'm not really interested in the vector P. I'm interested in psi. Okay, remember that the vector P had the modulus psi. Okay, and so dP divided by dt is actually d psi divided by dt projected on the unit vector in the direction of P plus psi d, the change of orientation of this vector with respect to time, P perpendicular, right? This is just classical formula for a vector that is turning. I'm interested in this part. So not only I'm inserting this in the integral, but I also project on the unit vector large P. It's pretty simple algebra. And that's why here you end up, and remember that the unit vector large P was in the orientation 0. So here I will have a cos of theta, and here this is only for psi, sorry. And this is a positive quantity, and here of course I have psi. This is a positive quantity. Why do I have psi? Well, psi is the integral of f times the orientation P of P. So you see that the diffusion, as expected, is always damping psi. It's minus something positive times psi. And you see that it's independent on the shape of the distribution. So I don't need any assumption on the distribution of the angle, which is a pretty nice thing. This is because what you do on the particles does not depend on its state. Of course, this is not the case when you start computing the other term. Can I erase this? Yes? Everybody? Okay, so now I want to do the same thing for what happened in a scattering event. In a scattering event, well, I don't know anything about this. I have to precise this. This will depend on the law that I give for the scattering. Elastic, inelastic, with rotation, no rotation. I mean, all the options that you like. Okay. Now, okay. This delta P, I can do the same trick. This delta P, I can also write it as its projection on the incoming P. Remember, there's the incoming small p. I can project the delta P on the incoming small p with modulus 1. So that will be this times P plus something times P perpendicular. Again, this is purely geometry. I mean, this problem you always have to deal a little bit with geometry. I will make the hypothesis that the scattering event does not contain rotation. So there will not be any component. I mean, there will not be any chirality in the scattering event from the make the story simple. But you could include it and compute everything also to see whether these particles would start rotating or not. So here you inject this as your little delta A scatter, and well, you don't get much. You just get 1 over lambda scattered, d psi over dt scattered will be this functional here applied to p delta p. So let's call this lambda phi scattered of delta A scattered. Then I didn't learn much. This will just be lambda scattered this is a function of delta p slash oops, oh, how did I call it? Not phi, not phi. That's not possible. Let's call it, I don't know, f. It's not nice, f? My big F is fine? Good. F scatter. Okay. And this one, this thing here, definitely depends on theta bar delta, because delta p is given by the rules of the collision. You know, when you write rule of collisions, it depends on the incoming angles of the particles. So these things here depends on this thing here. And so I cannot integrate out the distributions as I did for the diffusion. Now I have a quantity here that depends on the state of the particles before the collision. This is well known, okay? So I cannot do anything more if I don't tell you something about the distribution. That's the fate of kinetic theory. This is the celebrated closure problem in some sense. Okay, and here we are going to do something that is pretty nice. We're going to say, okay, if I knew the distribution perfectly well, then I would know psi, because I could integrate everything. Okay? Remember that psi is nothing but the modulus of the integral of the distribution times p of theta. I integrate all the orientation on the distribution, I take the modulus, this is psi. So if I knew the distribution, I would know psi. And I will make the following assumption. I will tell you, if I know psi, I know the distribution. Of course, it's not true. But that will be my ansatz. I will say, let's assume that my distribution, so that was first step, I would say, compute these two formula. Second step, I cannot go beyond without making an ansatz. My distribution f of theta t is entirely prescribed, or it's parametrized by a function. This is a gamma. A function that is parametrized by the instantaneous state of psi and is a function of theta. So I tell you, if I measure psi instantaneously, I know the distribution of the angle at that time. Okay. Now you see that if you have this, then you can inject it here. Okay. And what will happen from this quantity? Let's write it, and then I think it will be clear. I will get my integral between yes. Okay, I write it and then I explain. D delta over 2 pi, integral over this, the collision parameter, this kinetic kernel, and then some function that is a function of psi and delta, and then p delta p. And now it's not p hat anymore, and I will tell you why in a minute. I have to tell you what is g, otherwise I say nothing here. And g, I need another, yeah, and g of psi and delta is what happens when I've integrated over theta. It's 2 pi divided by, okay, 2 cosinus delta over 2. That's just because it's convenient. 1 integral over 0 and 2 pi d theta bar. This function gamma psi for theta bar plus delta over 2 times gamma psi theta bar minus delta 2. And then there is a cos theta bar here. Okay. So essentially, I've injected this ansatz over there, and I've performed the integration. Well, not perform, just move the integration of a theta bar inside. And now I have something like this. But you see that this is actually, so here, if I know my kinetic kernel, this is this integral here, and I know this function parameterized by psi. So this is, if I precise the shape of this function, you can integrate it. It's just a function of psi and delta. And now here what you have is that this equation that we have here, so this plus this Julien, how much time do I have? Minus 3 minutes. Okay. So I close here. So what do I have? I have that d psi over dt equal lambda diff d psi over dt diff, diffusion, plus lambda scatter d psi over dt scatter, with this one is very simple. It's minus a number, whatever you want to call it. I know my noise. This is a property of my model. So I know I can integrate this. So a number minus d psi, d is this number, plus is this number including the lambda diffusion, plus lambda scattered times this, and this is written here. It's this function here, where this is a function of psi only. So if I know everything about my collision rule, that is, I know how this depends on delta and zeta, I can, if I know my kinetic kernel, I will come back to that, I can integrate this, and it's a function of psi only. Okay? So this is lambda scatter, a function of psi only. And I conclude here. I have a closed nonlinear integral equation for my order parameter. Okay? And the only thing I needed was to say that the distribution is instantaneously parameterized by the value of the order parameter. Okay, I will close here. Then what we'll do next time is to say, well, then, to answer my initial problem, I will need to make some specific choice for this that will be pushing the ansatz a little bit more. I make now a specific choice for this dependence in theta. This is dangerous because we have to check then that it's true or close to reality. Then I can explicitly have this expression. It is a little bit complicated because it's integral, etc. But I'm only interested in the vicinity of psi equals 0. So I can linearize this part. By linearizing this part, I will have a first term proportional to psi. This term minus d is the quantity I was looking for at the very beginning of the lesson, by how much psi can grow or not. And I will have the answer for any kind of scattering interactions. And then precising the scattering interaction, V-check, inelastic active particles, my model of particle with the torque, any kind of things, we will compute this number, or numerically when we need to use numerics. Okay, thank you, and I will continue this on Friday. Yes, tomorrow.